The average temperature of the universe is 2.7 Kelvin. That is 2.7 degrees above the coldest condition physics permits. To put that in perspective, liquid nitrogen boils at 77 Kelvin. The cosmic average is roughly 29 times colder than that. Even liquid helium, the coldest cryogenic fluid commonly used in research laboratories, boils at 4.2 Kelvin. The universe runs colder than liquid helium across nearly its entire volume, and it has been cooling since the moment of its creation. But here is what most people misunderstand about that number. Space is not cold the way a winter night is cold. Cold air attacks you. It sends billions of nitrogen and oxygen molecules slamming into your skin every second, each collision pulling a tiny fragment of warmth from your body. That is conduction. That is temperature working the way human beings have experienced it for the entirety of evolutionary history. Space does not do that. Space does almost nothing at all. Temperature is a property of matter. It measures how fast particles move, how energetically they vibrate, how much kinetic energy they carry as they bounce around in random directions. In a gas, temperature describes the average energy of all those collisions. But the vacuum of space contains almost no matter to measure. A cubic centimeter of air at sea level holds roughly 25 billion molecules. A cubic centimeter of interstellar space might hold a single atom, possibly less. The concept of temperature barely applies to something so empty. You cannot measure the temperature of a vacuum with a conventional thermometer because there is nothing there to transfer energy to the instrument. This is the foundational confusion that distorts almost every popular description of the coldness of space. People imagine space as a freezer, a cold place you could enter and feel the cold pressing in around you. But a freezer is full of cold air, full of cold molecules doing exactly what cold molecules do, stealing energy through direct contact. Space has almost nothing to press against you. The vacuum offers no medium for conduction, no fluid for convection, and therefore no mechanism to actively drain your body heat. There are three ways heat moves from one object to another. The first is conduction, which requires direct physical contact between materials. The second is convection, which requires a fluid medium to circulate and carry thermal energy from one region to another. Convection drives ocean currents, stirs the atmosphere, and makes a breeze feel cooling on a summer afternoon. Both conduction and convection are irrelevant in space because both require matter in quantities that the vacuum does not provide. The third mechanism is radiation. Every object above absolute zero emits electromagnetic radiation. Your body radiates infrared light right now, streaming energy outward in every direction without any medium to carry it. The sun radiates visible light, ultraviolet light, and infrared radiation across a broad swath of the electromagnetic spectrum. This radiation travels through empty space at the speed of light without losing a single photon to friction. It does not need matter. It crosses billions of miles of perfect vacuum without any resistance whatsoever. Radiation is the only mechanism of heat transfer that works in space. And this single fact rewrites everything about how temperature operates beyond Earth's atmosphere. Consider an astronaut performing a spacewalk in low Earth orbit while the sun is shining. Solar radiation pours onto the sunlit side of the suit at roughly 1,360 watts per square meter. That is roughly the energy equivalent of pressing a space heater against every square meter of exposed surface. Without active cooling systems, the sunlit side of the suit can climb past 120 degrees Celsius. Hot enough to boil water. Hot enough to cause severe burns on unprotected skin. Now consider the shadowed side of that same astronaut. No direct solar radiation reaches it. The suit radiates its own heat outward, as infrared photons streaming into the void, with almost nothing coming in to replace the lost energy. Surface temperatures on the shadowed side can plunge below -100 degrees Celsius. In deep shadow, readings approaching -170 degrees Celsius have been recorded. Cold enough to shatter steel, cold enough to freeze human tissue in minutes. A single astronaut in orbit simultaneously experiences conditions separated by nearly 300 degrees Celsius from one side of their body to the other. Not because space has two different temperatures in those two directions. Space has no temperature at all in any meaningful sense in that region. The astronaut is simply caught between a powerful radiation source on one side and the complete absence of any radiation source on the other. The thermal environment is determined entirely by what shines on you and what you emit, not by any property of the surrounding vacuum. On Earth, air acts as a thermal buffer. Step from bright sunlight into deep shade on a summer afternoon and the air temperature barely changes. Convection mixes the atmosphere continuously, distributing heat and smoothing out extremes. The difference between sun and shade at ground level might be a degree or two. In space, there is no buffer, no smoothing, no atmospheric blanket. Radiation creates savage temperature gradients across distances as small as the width of a human body. Shadows in space are not gentle cool spots, they are thermal cliffs. The moon demonstrates this with unmistakable clarity. The lunar surface has no atmosphere, not a single molecule of protective gas between the ground and the void. When the sun illuminates the lunar equator during the roughly 2-week-long lunar day, the surface heats to approximately 127 degrees Celsius, hotter than boiling water. When that same surface rotates into the roughly 2-week-long lunar night, it cools to approximately minus 173 degrees Celsius. A swing of 300 degrees on the same patch of ground, driven entirely by the presence or absence of direct sunlight. Earth's most extreme desert environments experience temperature swings perhaps 5 or 6 times smaller, because the atmosphere absorbs, redistributes, and moderates the thermal extremes that would otherwise occur. Remove the atmosphere, and the surface becomes a killing ground of alternating extremes. This is why spacecraft engineering is fundamentally an exercise in thermal management rather than protection against cosmic cold. Engineers designing spacecraft do not think about the temperature of space. They think about thermal balance. Every spacecraft simultaneously absorbs solar radiation, absorbs radiation reflected off nearby planets and moons, absorbs the faint infrared glow of the cosmic background, and radiates its own thermal energy into the void. The spacecraft's temperature settles at whatever point incoming and outgoing energy flows reach equilibrium. The International Space Station uses enormous radiator arrays spanning roughly 2,500 square feet to dump excess heat generated by its own electrical systems, computers, lights, and the 6 human beings living inside it. Without those radiators, the station would overheat. Meanwhile, components in permanent shadow require electric heaters to prevent batteries from losing function and fuel lines from freezing solid. The station exists in perpetual contest between baking and freezing, managed continuously by thermal control systems that have been operating since the station was first assembled. The thermal indifference of space extends to every scale. The vacuum does not care about your temperature. It provides no moderation, no buffering, no protection against extremes. It simply allows radiation to pass through without interference, leaving every object to find its own thermal equilibrium through the balance of what it absorbs and what it emits. Now, step back from the engineering and think about the physics at cosmic scales. Between neighboring stars in our region of the Milky Way, the average separation is roughly 4 light-years. That is approximately 24 trillion miles of vacuum separating one sun from the next. Any object drifting through that interstellar space receives almost nothing in the way of radiation. The inverse square law governs how radiation intensity diminishes with distance. Doubling the distance from a star drops the received radiation to 1/4. Tripling it drops the radiation to 1/9. At 4 light-years from the nearest sun, the radiation from that star is so faint it would barely register on the most sensitive instruments ever built. An object floating in that void would radiate its own heat away, photon by photon, with almost nothing incoming to replace the lost energy. It would cool through the freezing point of water, through the freezing point of carbon dioxide, past the boiling point of liquid nitrogen, descending toward a floor set not by any local source but by the oldest, most diffuse radiation in the universe. That floor is the cosmic microwave background, a glow so faint no human eye could detect it, yet so perfectly uniform it fills every cubic centimeter of the observable cosmos without exception. Any object left alone in deep space, far from all stars and galaxies, will cool until it reaches thermal equilibrium with this background radiation. At that equilibrium, it absorbs as much energy from the background as it emits through its own thermal radiation. The cooling stops, and the temperature it settles at is approximately 2.7 Kelvin. 2.7 Kelvin is 2.7 degrees above absolute zero. In Celsius, that translates to approximately minus 270.45 degrees. In Fahrenheit, approximately minus 454.8 degrees. Absolute zero, 0 Kelvin, is the theoretical point at which all thermal motion ceases. Atoms stop vibrating. Molecules lock in place. Energy reaches its lowest possible quantum state. No physical process in nature has ever achieved true absolute zero, and the third law of thermodynamics establishes that reaching it precisely requires an infinite number of cooling steps. It is a limit that can be approached but never reached. 2.7 Kelvin sits so close to that limit that on any thermometer running from absolute zero to the surface temperature of the Sun, the cosmic baseline would be indistinguishable from the bottom of the scale. Consider the comparisons. Liquid nitrogen, the substance used to flash freeze biological samples, boils at 77 Kelvin. The cosmic background is roughly 29 times colder. Liquid helium boils at 4.2 Kelvin. The cosmic background is colder still. The coldest temperature ever recorded in Earth's natural environment was minus 89.2 degrees Celsius at the Soviet Vostok station in Antarctica on July 21, 1983. That translates to approximately 184 Kelvin. The cosmic background temperature is roughly 68 times colder than that Antarctic record. What humans consider the most extreme cold their planet can produce is close to room temperature compared to the thermal baseline of the cosmos. This number did not appear by accident. It is a relic of cosmic history. It is the fossil of an event that occurred nearly 14 billion years ago, transformed beyond recognition by nearly 14 billion years of cosmic expansion, and it carries within it the entire thermal biography of the universe. The universe did not always have this temperature. It was not always cold. In the earliest moments after the Big Bang, it was hotter than any object that currently exists in the observable cosmos. The story of how it reached 2.7 Kelvin is also the story of why that cold now dominates almost everything. Roughly 13.8 billion years ago, the universe as it exists today did not exist. There was no space, no time, no matter, no energy in any form that current physics can describe. Then the event called the Big Bang occurred. It was not an explosion within space. It was an explosion of space itself, the emergence of space-time from conditions that remain beyond the reach of existing physical theories. Space came into existence and immediately began expanding, carrying with it energy densities so extreme that no laboratory on Earth has come close to reproducing them. In the first fraction of a second, the entire observable universe, all the matter and energy that would eventually become hundreds of billions of galaxies, occupied a volume smaller than a single atom. The temperature in that primordial instant exceeded 10 trillion degrees. Every particle of matter and energy that would ultimately become stars, planets, oceans, and living organisms was compressed into a seething point of incomprehensible heat. The universe has been cooling ever since. In the first second after the Big Bang, the temperature plunged from those incomprehensible values to roughly 10 billion degrees. That sounds like catastrophic cooling, and it was. But 10 billion degrees is still hotter than the cores of the most massive stars burning in today's universe. The cosmos at 1 second old was a blazing plasma of protons, neutrons, electrons, photons, and neutrinos, all colliding with energies that would vaporize any structure that exists today. Photons could not travel any significant distance before colliding with a charged particle and scattering randomly. The universe was opaque. Light existed everywhere, but could propagate nowhere. Every direction was a wall of blazing fog. During the first 3 minutes, the temperature fell below 1 billion degrees, cool enough for protons and neutrons to begin fusing into the lightest atomic nuclei. Hydrogen nuclei form naturally as individual protons. Deuterium emerged when a proton and neutron stuck together. Helium nuclei assembled from pairs of protons and neutrons. Trace amounts of lithium appeared from slightly more complex reactions. This process, called Big Bang nucleosynthesis, lasted only a few minutes before the temperature dropped too low for fusion to continue. The cosmic forge shut down. The ratio of hydrogen to helium was locked in at approximately 75% hydrogen and 25% helium by mass, a ratio that observations of the oldest stars confirm with striking precision. But the universe was still extraordinarily hot. For hundreds of thousands of years after the Big Bang, temperatures remained above 3,000 degrees Kelvin, hot enough to keep all matter in a plasma state where electrons roamed freely without binding to atomic nuclei. Free electrons are phenomenally effective at scattering photons. Every time a photon encountered a free electron, it bounced off in a new direction. Light ricocheted through the plasma, trapped, unable to travel in straight lines. The universe was a uniform, glowing, opaque haze extending in all directions. Then, approximately 380,000 years after the Big Bang, the universe crossed a critical threshold. The temperature dropped below roughly 3,000 Kelvin. At that point, electrons lost enough energy to be captured by atomic nuclei. Protons grabbed electrons and became neutral hydrogen atoms. Helium nuclei captured their electrons. For the first time in cosmic history, matter became electrically neutral. The consequences were immediate and dramatic. Neutral atoms do not scatter photons the way free electrons do. When the electrons disappeared into atoms, the universe suddenly became transparent. The photons that had been trapped for hundreds of thousands of years were released all at once, free to travel in straight lines across the cosmos. This event is called recombination, and the moment of photon release is called the surface of last scattering. It represents the oldest electromagnetic signal the universe will ever produce. Those photons have been traveling ever since. They arrive at Earth from every direction in the sky. They fill every cubic centimeter of the observable universe. They are present in the room you are sitting in right now, everywhere, constant, ancient. But those photons do not arrive in the form they were released. When they left the surface of last scattering, they were visible light, roughly orange-red photons corresponding to a temperature of about 3,000 Kelvin. If you had been present at the moment of recombination and could somehow have survived the conditions, the entire sky in every direction would have glowed with a uniform deep reddish light. No shadows, no darkness, no contrast, just a continuous, omnidirectional glow. Since that moment, the universe has expanded by a factor of roughly 1100. Every photon traveling through space has been stretched along with it. Stretching increases wavelength. Longer wavelengths mean lower energy. Lower energy means lower effective temperature. The original visible light photons from recombination have been stretched so severely over billions of years that they now exist as microwaves. Their wavelength has increased from less than a micrometer to over a millimeter. Their effective temperature has dropped from 3,000 Kelvin to just 2.725 Kelvin. The entire sky still glows just as it did at recombination. But the glow has been shifted so far into the microwave spectrum that no biological eye in the universe could detect it. The cosmic microwave background is the afterglow of creation, dimmed and stretched by the expansion of space into invisibility. The discovery of this radiation is one of the great accidental triumphs in scientific history. In 1964, two radio astronomers at Bell Telephone Laboratories in Holmdel, New Jersey, were trying to use a large horn-shaped antenna for satellite communication experiments. Arno Penzias and Robert Wilson were meticulous engineers who wanted their antenna to be as sensitive as possible. They calibrated their equipment carefully. They accounted for radio interference from nearby New York City. They pointed the antenna away from known astronomical sources. They even climbed inside the horn and scraped out pigeon droppings, suspecting the birds nesting in the instrument might be contributing thermal noise to their signal. Nothing eliminated the problem. No matter what they did, a faint, persistent hiss remained in their data. It came from every direction equally. It did not change with the time of day. It did not change with the season. It did not change when they pointed the antenna at different parts of the sky. The signal corresponded to a thermal source at roughly 3.5 Kelvin, just a few degrees above absolute zero. Penzias and Wilson spent months searching for an explanation without success. The connection between their mysterious noise and the origin of the universe came from a group of theoretical physicists working just 40 miles away at Princeton University. Robert Dicke, Jim Peebles, and their colleagues had independently predicted that the Big Bang should have left behind a faint thermal radiation filling all of space. They were building their own antenna to search for this signal when they learned that Penzias and Wilson had already detected it by accident. The persistent hiss in the Bell Labs antenna was not instrument noise. It was not pigeon droppings. It was the remnant heat of the Big Bang itself, the oldest light in the universe, arriving at a radio antenna in New Jersey after a journey spanning nearly the entire history of cosmic time. Penzias and Wilson received the Nobel Prize in Physics in 1978 for a discovery they made while trying to eliminate what they thought was a nuisance. Over the following decades, increasingly sophisticated instruments refined the measurement. The Cosmic Background Explorer satellite, known as COBE, was launched by NASA in 1989 and carried instruments designed specifically to measure the cosmic microwave background from above Earth's atmosphere. COBE produced two groundbreaking results. First, it measured the spectrum of the background radiation and found that it matched the theoretical prediction for a perfect blackbody radiator with extraordinary precision. The match was the most perfect blackbody spectrum ever measured in nature, confirming that the radiation originated from a hot, dense, uniform early universe exactly as Big Bang theory predicted. The temperature was pinned down to 2.725 Kelvin with an uncertainty of less than 1,000th of a degree. Second, COBE detected tiny temperature fluctuations in the cosmic microwave background. The radiation was not perfectly uniform. Some directions in the sky were a few hundred thousandths of a degree warmer than average. Others were a few hundred thousandths of a degree cooler. These variations were about 1 part in 100,000, but their existence was revolutionary. They represented primordial density differences in the early universe, the seeds from which all cosmic structure would eventually grow. Regions that were slightly warmer at recombination were also slightly denser, and those density differences, amplified by gravity over billions of years, became the galaxies, galaxy clusters, and the entire large-scale structure of the cosmos. The Wilkinson Microwave Anisotropy Probe, launched in 2001, mapped the cosmic microwave background with roughly 35 times the angular resolution of COBE. The Planck satellite, launched in 2009 by the European Space Agency, pushed the measurements further still, observing at 9 different frequency bands with angular resolution and sensitivity that surpassed the previous mission by another significant margin. Planck refined the age of the universe to 13.798 billion years, confirmed the background temperature at 2.725 Kelvin, and measured the composition of the universe with percent-level precision. The proportions it established are remarkable. Ordinary matter, the atoms that make up stars, planets, and human beings, constitutes only about 4.6% of the total energy content of the cosmos. Dark matter accounts for roughly 23%. Dark energy, the mysterious component driving the accelerating expansion of space, makes up the remaining 72%. Nearly everything currently known about the large-scale properties of the universe derives from studying this ancient, faint, cold glow. The cosmic microwave background is also a cooling object. The universe continues to expand. As it does, the background photons continue to stretch and lose energy. Every passing day, the background temperature drops by an infinitesimal amount. In the far future, billions of years from now, the temperature will be lower still. A universe twice its current size will have a background temperature of roughly 1.4 Kelvin. A universe 10 times larger will glow at just 0.3 Kelvin. The afterglow of the Big Bang is a dying ember, slowly fading toward a darkness that can be approached but never fully reached, because absolute zero remains a physical limit rather than an achievable state. The universe spent its initial thermal inheritance in the first few 100,000 years. It has been running on fumes ever since, and the fumes are almost gone. The 2.7 Kelvin baseline tells you what happens in the absence of local energy sources. It tells you the temperature of the void, the empty stretches between galaxies where nothing shines and nothing burns. But the universe is not entirely empty. Scattered through the cosmic darkness are objects of extraordinary thermal intensity, stars that burn at millions of degrees in their cores. Accretion disks that reach temperatures rivaling the earliest moments of cosmic history. Nebulae glowing from the ultraviolet radiation of newborn stars. These structures create local thermal environments that deviate wildly from the background. The Sun maintains a surface temperature of approximately 5,500 degrees Celsius. Its core reaches 15 million degrees Celsius. These numbers exist on a completely different scale from the cold surrounding them. The Sun is not simply warm. It is a sustained thermonuclear explosion, a sphere of plasma held together by gravity and powered by the fusion of hydrogen into helium at pressures and temperatures that have no parallel anywhere in the natural universe except inside other stars. The Sun converts roughly 4 million tons of matter into pure energy every second. Not 4 million tons of fuel burned into ash, but 4 million tons of mass directly converted into photons through the relationship between energy and mass established by physics. That energy crosses 93 million miles of vacuum in about 8 minutes and arrives at Earth. Our Sun is not particularly impressive on the stellar scale. It is a middle-aged, medium-sized yellow dwarf. Blue supergiants like Rigel in the constellation Orion blaze with surface temperatures exceeding 11,000 degrees Celsius, roughly twice the temperature of the Sun's photosphere. Their cores can reach hundreds of millions of degrees, fusing helium, carbon, oxygen, and progressively heavier elements in nested shells of nuclear fire. The most massive stars known, weighing over 100 times the mass of the Sun, burn through their fuel with such ferocity that their entire lives span only a few million years, compared to the Sun's expected 10 billion-year lifespan. These stellar giants live briefly, burn outrageously hot, and die in cataclysmic explosions that briefly outshine entire galaxies. On the opposite end of the stellar spectrum, red dwarfs burn cool and slow. Their surface temperatures hover around 3,000 degrees Celsius, dim compared to the Sun but still thousands of times hotter than the cosmic background. Red dwarfs are the most common type of star in the universe, comprising roughly 70% of all stars in the Milky Way. Yet they are so dim that not a single red dwarf is visible to the naked eye from Earth, despite being the most numerous stellar objects in the galactic census. They burn their fuel so sparingly that their lifespans extend into the trillions of years. Every red dwarf that has ever ignited is still burning today. Not one has yet exhausted its fuel. These patient, dim furnaces will be the last sources of stellar warmth the universe ever produces. When matter falls toward a black hole, it spirals inward through an accretion disk, a swirling vortex of gas and dust compressed by gravitational forces so intense that the material heats to extraordinary temperatures. The inner regions of accretion disks around stellar mass black holes can reach tens of millions of degrees. Around supermassive black holes at the centers of galaxies, weighing millions or billions of solar masses, accretion disk temperatures climb into the hundreds of millions of degrees. The most extreme accretion environments found in quasars, the luminous cores of distant active galaxies, produce temperatures approaching 1 billion degrees or more. Supernova explosions briefly exceed even these temperatures. When a massive star exhausts its nuclear fuel, its iron core collapses in a fraction of a second. The implosion rebounds off the impossibly dense collapsing material, sending a shock wave outward through the star's outer layers with an energy output that briefly rivals the total luminous power of the observable universe in neutrinos alone. The temperature at the collapsing core reaches roughly 100 billion degrees for a violent instant. That is hotter than the interior of any stable star, hotter than any accretion disk, hotter than the universe has been at any point since the first second after the Big Bang. In that moment, a dying star briefly recreates conditions that existed when the cosmos was less than 1 second old. But then it fades. The heat disperses. The expanding remnant cools over thousands of years, eventually merging with the cold interstellar medium. The thermal violence is spectacular but fleeting. All of these hot objects, from stellar cores to quasar accretion disks to supernova remnants, share one critical characteristic. They are vanishingly small compared to the cold space that contains them. Consider the geometry. The Sun spans roughly 865,000 miles in diameter. The nearest star, Proxima Centauri, sits 4.25 light-years away, approximately 25 trillion miles of vacuum separating one stellar furnace from the next. If you shrank the Sun to the size of a ping-pong ball, Proxima Centauri would be another ping-pong ball sitting approximately 720 miles away. Between those two tiny spheres lies nothing. 720 miles of empty space. Two specks of warmth separated by a wasteland that dwarfs them by a factor of roughly 30 million. The Milky Way contains an estimated 200 to 400 billion stars. That sounds impressive until you account for the volume they occupy. The galaxy spans roughly 100,000 light-years across and 1,000 light-years thick. Its total volume is approximately 8 trillion cubic light-years. Dividing that volume by the number of stars means each star commands on average a private empire of roughly 20 to 40 cubic light-years of empty space. Stars are separated by distances so disproportionate to their sizes that the galaxy is almost entirely vacuum. If you stood outside the Milky Way and could resolve individual stars, you would see mostly darkness punctuated by scattered points of light, like a handful of fireflies released into a football stadium at night. The stadium is real. The fireflies are real. But the defining characteristic of the scene is the darkness between them, not the specks of light. The Sun's thermal influence extends outward into the void, but only so far. The habitable zone, the orbital band where liquid water can persist on a rocky planetary surface, spans a narrow ring between roughly 0.95 and 1.7 astronomical units from the Sun. That ring is roughly 70 million miles wide. It sounds substantial until you hold it against the 4 light-year gulf to the next star. Compared to the distance between neighboring stars, the habitable zone occupies less than 1/1,000,000,000% of the space between them. The warm zone around each star is a microscopic dot embedded in a cold void extending for trillions of miles in every direction. Earth sits within that dot. Every living thing that has ever existed on this planet depends on continued placement within that dot. Now zoom further out. Galaxies are not distributed evenly through the universe. They cluster along vast filaments and walls called the cosmic web, a structure shaped by gravity acting on the primordial density variations recorded in the cosmic microwave background. Where filaments intersect, galaxy clusters form. Dense knots of thousands of galaxies bound together by gravity and surrounded by superheated gas. Between these filaments stretch cosmic voids, enormous regions of space containing almost no galaxies at all. These voids are the dominant feature of the universe's large-scale structure. A typical cosmic void spans 100 to 300 million light-years across. The largest known voids exceed 1 billion light-years in diameter. The Boötes void, one of the first supervoids discovered, stretches roughly 330 million light-years, while containing fewer than 60 known galaxies in its interior. To appreciate that emptiness, consider that our local group of galaxies contains over 50 galaxies packed into a region just 10 million light-years across. The Boötes void is 33 times wider and contains roughly the same number of galaxies. If Earth were located at the center of the Boötes void rather than in its current position, astronomers would not have discovered the existence of external galaxies until far more powerful telescopes were developed. The night sky would have been nearly featureless beyond the stars of our own galaxy. Scientists estimate that cosmic voids occupy approximately 80 to 90% of the total volume of the observable universe. The filaments, walls, clusters, and galaxies where stars actually burn are crowded into the remaining 10 to 20%. This means that if you selected a random point anywhere in the observable universe, the overwhelming probability is that you would find yourself in a void, far from any galaxy, far from any star, surrounded by nothing but the 2.7 Kelvin glow of the cosmic microwave background stretching to the horizon in every direction. Even within the filaments where galaxies concentrate, most of the volume remains cold. Galaxies themselves are mostly empty space. The interstellar medium, the gas and dust between stars, occupies temperatures ranging from roughly 50 Kelvin in cold molecular clouds to 10,000 Kelvin in ionized regions around hot stars. But this material is so thinly spread that its thermal contribution to the surrounding vacuum is minimal. Walk a straight line through the Milky Way in any random direction, and you would pass through light years of near vacuum for every fraction of a second spent inside the atmosphere of a star. The observable universe has a radius of approximately 46.5 billion light-years. Its total volume is roughly 4.2 times 10 to the 80th power cubic meters. The total volume of all stellar interiors in the observable universe, representing roughly 10 to the 24th power stars, each with an average volume somewhat smaller than the Sun, comes to approximately 10 to the 51st power cubic meters. Divide stellar volume by total cosmic volume, and you get a fraction on the order of 10 to the negative 29th power. The hot interiors of stars occupy less than 1 billionth of 1 billionth of 1 billionth of the total volume of space. The rest is vacuum at or near the cosmic microwave background temperature. Warm matter is not rare in the universe. It is essentially non-existent when measured as a fraction of cosmic volume. There is an important distinction that prevents even the hot intergalactic gas from changing this conclusion. Between galaxy clusters, thin strands of gas thread through the cosmic web along filaments. Some of this material reaches temperatures of 100,000 to 10 million Kelvin, heated by gravitational shocks during the process of structure formation. This warm, hot intergalactic medium contains a significant fraction of all ordinary matter in the universe. But the temperature of a gas measures the average kinetic energy of its individual particles. A gas can have a very high temperature while simultaneously having an extremely low density. High temperature combined with low density means very little thermal energy per unit volume. The intergalactic medium may be technically hot in terms of particle velocity, but it is so sparse that a cubic meter of this material contains only a handful of particles. Standing inside it, you would feel nothing. No warmth whatsoever. Your body would still radiate heat into the void and receive almost nothing in return, regardless of whether the surrounding particles happen to be moving at velocities corresponding to millions of degrees. Temperature and thermal energy are not the same thing. Temperature describes the state of whatever matter is present. Thermal energy depends on how much matter exists at that temperature. A single particle moving at velocities corresponding to 1 million degrees carries an almost unmeasurably tiny amount of actual energy. A room full of air at 20 degrees Celsius contains astronomically more thermal energy than a cubic light year of intergalactic plasma at 10 million degrees. The intergalactic medium is hot in name only. This distinction is essential for understanding why the universe can contain stars at millions of degrees, accretion disks at billions of degrees, and intergalactic gas at millions of degrees, yet remain overwhelmingly and completely cold. The hot stuff is either too small or too sparse to matter thermally at cosmic scales. The cold vacuum wins not because it is powerful, but because it is everywhere, in vastly greater quantity than all the heat in all the stars and all the galaxies combined. Now introduce time to this picture, and the dominance of cold becomes even more absolute. The universe has existed for 13.8 billion years. Stars have been burning for roughly 13.5 billion of those years, since the first generation ignited from primordial hydrogen a few 100 million years after the Big Bang. But stars will not burn forever. The supply of hydrogen available for nuclear fusion is finite. It is being consumed in stellar cores across every galaxy and will never be replenished by any known physical process. New stars still form in the Milky Way at a rate of roughly 3 solar masses of new stellar material per year. But the rate of star formation has been declining since its peak roughly 10 billion years ago. The universe is past its stellar prime. The golden age of star formation is behind us. Each passing billion years sees fewer new stars born than the billion years before. Red dwarfs, the most frugal stellar consumers, will persist longest. Their internal convection fully mixes their hydrogen fuel, allowing them to burn through nearly their entire mass rather than just the core, as larger stars do. The most miserly red dwarfs will burn steadily for perhaps 10 to 15 trillion years before exhausting their supply. That is roughly 1,000 times the current age of the universe. After the last red dwarf sputters out, no new stars will ignite. The raw material will have been consumed or dispersed beyond recovery. The universe will enter what physicists call the degenerate era, dominated by the cooling remnants of dead stars. White dwarfs, the compressed cores left behind when stars like our Sun exhaust their fuel, will cool slowly over trillions of years. They begin their afterlives glowing intensely with residual heat, some initially hotter than the surfaces of the most massive living stars. But they produce no new energy. They are embers, not fires. Over time, scales measured in quadrillions of years, they will fade from dim yellow to deep red to infrared to microwave radiation, finally reaching an equilibrium temperature indistinguishable from the cosmic background. Each cooling white dwarf reenacts the universe's own thermal history in miniature. Born hot, fading slowly, approaching but never quite reaching absolute cold. Black holes will dominate the mass budget of the far future cosmos, slowly evaporating through Hawking radiation over timescales that make the stellar era look like the flash of a camera. A stellar mass black hole takes roughly 10 to the 67th power years to evaporate completely. A supermassive black hole at the center of a galaxy requires roughly 10 to the 100th power years. When the final black hole evaporates in a faint burst of radiation, the universe will contain nothing but diffuse particles and photons, drifting apart in an expanding void that grows colder with every passing moment. Measured against this cosmic timeline, the era of starlight is a brief flicker. The stelliferous era, the period during which stars exist and shine, spans roughly 100 trillion years at most. That sounds like an eternity by human standards. But the eras that follow extend across timescales so much longer that the stelliferous era shrinks to a rounding error. If you represented the entire future history of the universe as a single calendar year, with the Big Bang at the start of January 1st and the evaporation of the last black hole at the end of December 31st, the entire era of starlight would occupy the first fraction of a millionth of a second after midnight on January 1st. The rest of the year, every month, every week, every day, every hour, every remaining second would pass in total darkness at temperatures approaching absolute zero. The warm era is not just brief. It is so brief compared to the cold future that calling it brief is itself an understatement. The universe will spend the overwhelming majority of its existence in total darkness and total cold. Stars are a temporary phenomenon. The warmth they provide is a temporary gift. The conditions they create for biology are temporary shelters against an eternal cold that will eventually reclaim everything. Every living thing that has ever existed on Earth or on any other world in any galaxy exists during this narrow window when the universe still produces light and heat. What this means for our understanding of where we fit in the cosmos requires holding all of these scales together at once. The observable universe contains roughly 2 trillion galaxies. Each harbors its own population of stars, its own scattering of planetary systems, its own vanishingly thin habitable zones surrounding isolated stellar furnaces. The total number of potentially warm habitable worlds across all observable galaxies might reach into the tens of billions. A number so large it sounds hopeful until you remember the denominator. The total volume of the observable universe is approximately 4.2 times 10 to the 80th power cubic meters. The combined volume of every habitable zone around every star in every galaxy is a fraction so small that even scientific notation struggles to convey its insignificance. A single warm, habitable, life-supporting world requires a remarkable convergence of conditions. It needs a star of the right mass burning at the right rate, emitting the right spectrum of radiation to heat a rocky planet without sterilizing it. The Sun has delivered this with remarkable stability over 4.5 billion years. A star 10% more massive would burn hotter and die sooner, possibly before complex life had time to evolve. A star 20% less massive would emit most of its energy as infrared radiation, altering the atmospheric chemistry of any world warmed by it. Even with the right star, a planet must orbit at precisely the right distance. A few percent closer and oceans evaporate. A few percent farther and they freeze. This habitable zone is so narrow relative to the full extent of a planetary system that it occupies a ring smaller than the gap between Jupiter and Saturn. Earth threads this needle. Even orbital distance is insufficient. Earth requires an atmosphere. Without one, the surface would swing between lethal extremes with every rotation, baking in direct sunlight and freezing in shadow, just as the moon does. Earth's atmosphere traps infrared radiation through the greenhouse effect. and redistributes heat from the equator toward the poles through convection. Without it, Earth's average surface temperature would hover around -18 degrees Celsius, cold enough to freeze the ocean solid. The greenhouse effect, driven primarily by water vapor and carbon dioxide, raises the average to approximately 15 degrees Celsius, a difference of 33 degrees that transforms a frozen rock into a living world. The atmosphere itself depends on Earth's mass being large enough to gravitationally retain a substantial gas envelope against the erosion of solar wind, but not so large that it accumulated a thick hydrogen and helium atmosphere like Jupiter. It depends on Earth's magnetic field, generated by convection currents in a liquid iron core, being strong enough to deflect the charged particles from the Sun that would otherwise gradually strip the atmosphere away. Mars likely lost much of its atmosphere through exactly this mechanism. Its magnetic field faded as its core cooled, leaving the solar wind to slowly erode whatever protective atmosphere it had once possessed. Mars was probably warm once. It is not warm now. Layer these requirements together, and the picture of what warmth actually requires becomes clear. The right star, the right orbital distance, the right planetary mass, the right atmosphere. The right magnetic field? The right geological activity to cycle carbon and regulate surface temperature over billions of years. The right amount of water. The right kind of large outer planet to deflect incoming asteroids and comets that would otherwise bombard the inner planets with sterilizing frequency. Each requirement is itself the product of a chain of physical events stretching back through the formation of the solar system, through the stellar generations that preceded our Sun, through the galaxy formation process, through the density fluctuations in the early universe that seeded those galaxies in the first place. Pull any single link from that chain and the rest collapses. The warmth you experience at this moment is the end product of a chain extending backward through 4 billion years of planetary history, 5 billion years of stellar evolution, and 13.8 billion years of cosmic expansion. None of it was guaranteed. Physics did not mandate a warm Earth. The equations that govern the universe are indifferent to whether any particular rock orbiting any particular star happens to fall within a temperature range compatible with liquid water. The warmth exists because of how things happen to unfold. The second law of thermodynamics guarantees that energy moves from concentrated to diffuse, from hot to cold, from ordered to disordered. Stars resist this trend locally by fusing hydrogen under gravitational pressure. Life resists it locally by building complex molecules from simple ones. But both are local and temporary reversals of a universal trend. The trend points toward equilibrium, and equilibrium at cosmic scales means cold. It means 2.7 Kelvin and eventually even less than that. Stars do not save the universe from cold. Every star that shines is converting matter into energy and radiating that energy into the void, where it dilutes, stretches, and cools. The very process that creates warmth locally contributes to the ultimate triumph of cold universally. Stars are afterthoughts in the thermal ledger of the cosmos, brilliant, essential for the existence of anyone capable of asking about temperatures. But afterthoughts nonetheless. The main product of cosmic evolution is empty, cold, silent vacuum. In roughly 1 billion years, the gradually increasing luminosity of the Sun will have risen by approximately 10%, enough to trigger a runaway greenhouse effect that boils Earth's oceans and renders the surface uninhabitable. The warmth that has sustained biology for 4 billion years will become the heat that destroys it. Even the Sun's gift comes with an expiration date printed in the physics of stellar evolution. The universe is in the most literal physical sense a machine for producing cold, not because it was designed to be cold. There is no intent, no plan, no purpose behind the thermal emptiness. It simply follows physical laws that, applied to the actual distribution of matter and energy across cosmic volumes and cosmic timescales, inevitably produce a cosmos where warmth is the exception and cold is everything else. What this proportionality ultimately reveals is not just a fact about physics. It is a fact about the conditions of existence itself. We live in a thermal outlier, a statistical extreme. A pocket of warmth so improbable against the backdrop of cosmic cold that its existence demands recognition, not with fear or despair, but with accurate perception. The warm, habitable, life-permitting conditions you experience every day on the surface of this planet represent a cosmic anomaly so extreme that the universe, if it could be said to have a default state, would not recognize our environment as remotely normal. The warmth of Earth is not permanent. It is not the natural state of things. It is a gift from a particular star at a particular distance during a particular epoch of cosmic history. The Sun has roughly 5 billion years of stable hydrogen burning remaining. After that, it will swell into a red giant, expanding its outer layers past the orbit of Venus, scorching the inner solar system into uninhabitable ruin. But long before that, the universe will continue cooling. The cosmic microwave background will continue fading. The era of stars will end. The era of cold remnants will begin. And the cold that already occupies 80 to 90% of cosmic volume and will eventually occupy effectively all of it will continue, unchanged and indifferent, across timescales that make the current age of the universe seem like a brief introduction. The truly striking fact is not the number 2.7 Kelvin, though that number is harrowing enough on its own. The truly striking fact is the proportion. Warmth, the condition that makes you possible, occupies an almost immeasurably small fraction of all that is. The cold is not surrounding warmth the way darkness surrounds a campfire, with the fire holding its own. The cold is the darkness. It is everything. And the warmth of Earth, of oceans, of biological chemistry, of conscious experience contemplating its own improbability, is a local and temporary exception that the universe has never needed to fight against. It simply needs to wait. This is where the science stops and the open questions begin. Researchers studying the cosmic microwave background continue refining our understanding of what the early universe looked like and what forces drove its initial expansion. The patterns of temperature fluctuations in the background radiation encode information about events that occurred in the first trillionth of a second after the Big Bang. Timescales and energy scales that lie beyond the reach of any particle accelerator ever built or proposed. Future missions may push the measurements of the background to even higher precision, searching for the imprint of primordial gravitational waves that would confirm or constrain specific models of cosmic inflation. The James Webb Space Telescope is currently analyzing the atmospheres of exoplanets, searching for chemical signatures that might indicate habitable or inhabited conditions. This work will take decades and will require confirmation from multiple independent techniques before any conclusions about life beyond Earth can be considered established. But the data being gathered now may eventually allow scientists to estimate how many worlds, if any, have maintained warm, habitable conditions long enough for biology to develop. The physics of the far future, the cooling and eventual evaporation of stellar remnants and black holes, remains an area of active theoretical investigation. Hawking radiation has not yet been directly detected. The physics governing the final moments of black hole evaporation is not fully understood and may require a theory of quantum gravity that does not yet exist. The ultimate fate of matter, whether protons are stable over the timescales required for the degenerate era, or whether they eventually decay, remains an open experimental question. Experiments designed to detect proton decay have been running for decades without observing any events, placing increasingly tight constraints on the proton lifetime, but not yet resolving the question definitively. The relationship between the thermal history of the universe and the emergence of complexity, life, and consciousness is perhaps the deepest open question of all. The conditions that make biology possible represent a narrow slice of the thermal landscape of the cosmos. That slice exists only during the stelliferous era, only within the habitable zones of suitable stars, and only on planets whose geological and atmospheric histories have remained within the relevant temperature range long enough for evolution to work. Whether those conditions are common enough that life is widespread in the cosmos, or so rare that Earth represents something genuinely singular, remains unknown. What is known is the basic thermal fact at the center of this entire story. The universe defaults to cold. It has been cooling since its birth. It will continue cooling until its last sources of heat exhaust themselves and fade. The warm era is a brief, bright interval between a cold past and a colder future. Every sunrise you experience, every ocean that remains liquid, every living cell that maintains its temperature through metabolism, is a local and temporary exception to a universal rule that has never stopped operating and will never stop operating until the last photon stretches into irrelevance in an expanding void with nothing left to illuminate. The cold is the universe's true nature, the warmth is the surprise, and the surprise, fragile and temporary and rare beyond calculation, is where everything we know about existence happens to have taken place. To truly appreciate the depth of cosmic cold, it helps to walk carefully through the temperature scales involved and place familiar objects along them in order to understand what 2.7 Kelvin actually means when held against the full range of thermal experience. Absolute zero, 0 Kelvin, is the bottom of the scale. Below it, nothing exists. It is not simply the coldest achievable temperature. It is the temperature at which all thermal motion ceases entirely. Atoms stop vibrating. The quantum mechanical ground state of energy is reached. No physical process has ever achieved this state because the third law of thermodynamics establishes that reducing the temperature of any finite system to absolute zero requires an infinite number of steps. Every cooling operation, no matter how efficient, only asymptotically approaches the limit without reaching it. Absolute zero is a boundary, not a destination. Moving up from zero, the first notable benchmark in the natural cosmos is the cosmic microwave background at 2.725 Kelvin. This is the temperature floor of the universe. No passive object in space can cool below this value through natural processes. The background radiation bathes everything in a minimum energy input that maintains this floor everywhere across the observable cosmos. At 4.2 Kelvin, liquid helium transitions from liquid to gas. Helium has the lowest boiling point of any element. It remains liquid at temperatures where every other substance has long since solidified. To produce liquid helium, specialized cryogenic equipment consuming substantial electrical energy is required. The universe achieves temperatures equal to or colder than liquid helium across the overwhelming majority of its volume, passively, by simply being empty. At 77 Kelvin, liquid nitrogen boils. Liquid nitrogen is the workhorse of laboratory cryogenics. It is used to flash freeze biological samples, conduct low-temperature experiments, and cool sensitive instruments. Its temperature seems extremely cold by everyday standards, but it is roughly 29 times warmer than the cosmic microwave background. At 184 Kelvin, approximately -89 degrees Celsius, you reach the coldest temperature ever recorded in Earth's natural environment. That Antarctic measurement at the Soviet Vostok Research Station in 1983 represents the absolute thermal extreme of Earth's most hostile region. It would be lethal to an unprotected human being in minutes. Yet it is 68 times warmer than the temperature that dominates the universe. At 273 Kelvin, water freezes. This is 0 degrees Celsius, the conventional reference point for the Celsius temperature scale. The average temperature of Earth's surface sits roughly 15 degrees Celsius above this value, meaning roughly 288 Kelvin. Human body temperature sits at approximately 310 Kelvin. These temperatures, which feel ordinary and unremarkable because they are what life evolved within, are in the context of the cosmos extraordinarily unusual. They represent conditions found in a negligibly small fraction of cosmic space. Moving further up the scale, the surface temperature of the Sun sits at approximately 5,778 Kelvin. The photosphere, the visible surface layer of our star, sustains a temperature that would vaporize every known material in seconds. Yet this temperature is simply where the Sun's convective outer layers release their energy into space. Deeper inside, the Sun becomes dramatically hotter. At the base of the Sun's convective zone, roughly 200,000 kilometers below the visible surface, temperatures reach approximately 2 million Kelvin. In the radiative zone below that, temperatures climb further. At the core, where hydrogen fusion actually occurs, the temperature reaches approximately 15 million Kelvin. At these temperatures, matter exists as plasma, a state in which electrons have been stripped completely away from atomic nuclei by the extreme thermal energy. Hydrogen nuclei, bare protons, collide with sufficient energy to overcome their mutual electromagnetic repulsion and fuse, releasing the energy that sustains the Sun. The most massive and hottest stars reach core temperatures far exceeding the Sun. Blue supergiants fuse progressively heavier elements as they age, requiring increasingly higher temperatures for each stage of fusion. Carbon fusion occurs at roughly 500 million Kelvin. Oxygen fusion requires about 1 billion Kelvin. Silicon fusion, the final stage before an iron core forms and the star faces catastrophic collapse, occurs at temperatures around 3 billion Kelvin. And then the collapse itself temporarily exceeds all of these values. When a massive star's iron core implodes in a fraction of a second, the density and temperature at the collapsing center briefly reach conditions that have not existed since the first second of the universe. Temperatures of 100 billion Kelvin, densities comparable to atomic nuclei, energy densities that briefly reconstruct something approaching the primordial plasma of the Big Bang itself. The violence is real and extraordinary, and it lasts for a moment before the star tears itself apart and the heat dissipates into the expanding remnant. The accretion disks around the most active supermassive black holes, the structures powering quasars, represent the hottest sustained environments in the modern universe. Temperatures in the innermost regions of these disks can approach several billion Kelvin. The radiation output of the most luminous quasars can exceed the combined light of an entire galaxy by factors of tens or hundreds. These objects are visible across billions of light-years of intergalactic space because of the sheer thermal ferocity of material being pulled inexorably into a gravitational singularity. Yet even these extremes, as spectacular as they are, occupy a fraction of cosmic volume so small they do not meaningfully change the thermal accounting. The hot objects are real. They are among the most dramatic phenomena in nature. But they are islands in a cold sea so vast that all their fire cannot warm the void that contains them. The structure of that void is worth examining in more detail because the emptiness between the hot objects is not uniform. It has its own thermal architecture that reveals additional layers of the universe's coldness. The interstellar medium within galaxies varies considerably in temperature depending on the local environment. In the cold neutral medium, regions of neutral hydrogen gas far from any hot stars, temperatures range from roughly 50 to 100 Kelvin. These regions are cold enough to allow complex molecules to form. Carbon monoxide, water ice, ammonia, methanol, formaldehyde, and hundreds of other organic and inorganic molecules have been detected in the cold regions of the interstellar medium. These molecular clouds are typically colder than most laboratory cryogenic equipment and represent the coldest large-scale environments within galaxies. Within molecular clouds, the coldest pockets, the so-called dense cores where new stars will eventually form, can reach temperatures as low as 10 Kelvin, barely above the cosmic microwave background. These regions are shielded from the ultraviolet radiation of nearby stars by dense layers of dust and gas, allowing them to cool almost to the universal baseline. The paradox that the coldest regions inside galaxies are precisely where new stars are being born is one of the most elegant ironies in astrophysics. The cold cores collapse under their own gravity, and as the collapsing gas compresses, it heats. What begins as a 10 Kelvin cloud can become a star burning at millions of degrees in its core within a few million years, extreme cold giving birth to extreme heat. The warm neutral medium, regions where stellar radiation heats the gas without fully ionizing it, sits at roughly 6,000 Kelvin. The hot ionized medium surrounding hot young stars and supernova remnants reaches 10,000 Kelvin or higher. The coronal gas heated by supernova shocks reaches temperatures of 1 million Kelvin or more. These different phases of the interstellar medium coexist in a complex turbulent mixture driven by the ongoing processes of star formation, stellar evolution, and stellar death. Even so, the density of the interstellar medium is so low that none of these hot phases contribute meaningfully to the thermal environment of space in the way a room full of air contributes to the thermal environment of a building. A cubic centimeter of hot ionized interstellar gas at 1 million Kelvin contains only a few atoms. Those atoms carry very little total thermal energy despite their high individual velocities. The space around them is functionally the same temperature as anywhere else in the void. 2.7 Kelvin from the cosmic background, with the hot gas particles moving through it without warming it in any practical sense. The distinction between temperature and heat that this illustrates has been one of the most important conceptual tools in thermal physics since the 19th century, when James Clerk Maxwell and Ludwig Boltzmann developed the kinetic theory of gases. Temperature is a statistical property of a collection of particles. It describes the average kinetic energy per particle. But heat, the quantity that actually transfers between objects in contact, depends on the total thermal energy available. A tiny quantity of very hot gas carries less total thermal energy than a large quantity of warm gas. The vacuum of space may contain particles moving at velocities corresponding to millions of degrees, but it contains so few particles that the total thermal energy in any given volume is negligible. This mathematical reality allows the universe to be simultaneously hot in some of its particles and cold in its practical thermal character. The cosmos is not deceptive. The physics is consistent. But the words we use for temperature can mislead when applied carelessly to environments where matter is present in quantities so small they barely influence the thermal conditions experienced by any real object. The cosmic web, the large-scale structure that distributes galaxies into filaments and voids, also encodes the thermal history of cosmic evolution in ways that researchers continue to investigate. The hot gas in galaxy clusters, heated to tens of millions of Kelvin by the gravitational compression of enormous mass, forms the intracluster medium. This gas is so hot it radiates in X-rays and can be detected by space-based X-ray telescopes like Chandra and XMM Newton. Mapping the distribution of this hot gas reveals the distribution of mass throughout the cluster, including the dark matter that dominates the gravitational structure but emits no light of its own. The filaments connecting galaxy clusters also contain hot gas, the warm-hot intergalactic medium discussed earlier. Detecting this gas has been challenging because it is spread too thinly to produce strong signals, but observations using the Sunyaev-Zeldovich effect, in which the hot electrons in the gas slightly distort the cosmic microwave background photons passing through it, have allowed astronomers to map the distribution of gas along filaments between clusters. This technique essentially uses the cosmic microwave background as a backlight and the hot intergalactic gas as a filter, revealing the thermal structure of the cosmic web in projection across the sky. The cosmic microwave background is useful not just as a source of information about the early universe and the large-scale distribution of matter. It also serves as a precise thermometer for the temperature of the universe at different epochs. By studying the spectra of distant quasars, astronomers can detect the signature of microwave background photons at the time they interacted with gas along the line of sight. The temperature of the background radiation at different distances, corresponding to different times in cosmic history, can be measured by these techniques, and the results confirm the expected cooling trend. The background was hotter in the past when the universe was smaller and denser, and it is cooling as the universe expands, exactly as the Big Bang model predicts. This agreement between prediction and measurement over billions of years of cosmic history represents one of the most powerful confirmations of the standard cosmological model. The future of the cosmic microwave background is equally important to the long-term thermal picture. As the universe continues expanding, the background will cool below 2 Kelvin, then below 1 Kelvin, then into fractions of a degree above absolute zero, approaching but never reaching the absolute limit. There is no process in the known universe that will add energy to the background to prevent its continued cooling. The expansion is accelerating, driven by dark energy, which means the rate at which the background cools is itself increasing. The future of cosmic cold is not a slow drift toward lower temperatures, but an accelerating plunge. Long after the last stars have burned out and the last white dwarfs have faded to darkness, the cosmic microwave background will still exist, grown colder than anything that will be left to measure it. The universe will be a vast expanse of nearly perfect cold, populated only by isolated black holes slowly evaporating, cooling white dwarfs fading to black, and diffuse particles drifting apart in an expanding void. The background temperature of this remote future will be so low that no instrument consistent with known physics could distinguish it from absolute zero. The question of whether any form of information processing, and by extension any form of experience, could persist in such an environment has been explored theoretically. The physicist Freeman Dyson proposed in 1979 that life of a sufficiently advanced form might adapt to the cooling universe by slowing its metabolism and hibernating for increasingly long periods between activity. preserving the total amount of thought and experience through an infinite future. But subsequent analysis, particularly by the physicist Frank Tipler, and later by others examining the implications of dark energy and accelerating expansion, suggested that even this possibility is foreclosed. The accelerating expansion driven by dark energy appears to place hard limits on the amount of energy that can ever be harnessed by any finite region of space, setting a maximum on the total amount of information processing possible in the future of the universe. These are speculative questions at the frontier of theoretical physics and cosmology, but they illustrate how the fundamental coldness of the universe connects to questions about the long-term possibilities of existence itself. The thermal future of the cosmos is not merely a background fact about physics, it is a constraint on everything that could ever happen. To ground all of this in the human scale, consider what the thermometric reality of space meant for the early history of spaceflight, when engineers first had to confront the alien thermal environment of orbit. The first artificial satellite, Sputnik 1, launched by the Soviet Union in October of 1957, experienced temperatures that alarmed engineers on the ground. Without careful thermal management, components inside the satellite overheated on the sunlit side of the orbit and chilled dangerously on the dark side. The satellite had to be designed with reflective coatings, thermal conductors to move heat between compartments, and careful consideration of which components were exposed to direct sunlight and for how long. The American Explorer 1 satellite, launched in early 1958, carried temperature sensors that measured the thermal environment directly. The data confirmed what theory predicted. The satellite experienced dramatic temperature swings with each 90-minute orbit, swings that would have been far more severe had the spacecraft not been deliberately designed to moderate them. The Mercury, Gemini, and Apollo programs that followed required increasingly sophisticated thermal management as the missions grew more complex and the astronauts spent more time in space. The Apollo command modules used multi-layer insulation blankets, reflective external surfaces, and active temperature control systems that circulated coolant through the walls to maintain habitable conditions inside despite the extreme external temperature variations. The Apollo missions to the lunar surface faced the additional challenge of managing equipment during the 2-week-long lunar night. Scientific instruments left on the surface had to be designed to survive temperatures approaching -170°C during the night and then operate normally when the sun rose and the surface heated to over 100°C. The temperature range exceeded the specifications of most standard commercial electronics by a factor of several times, requiring specially designed materials and careful thermal engineering at every component level. The engineering lessons learned during the early space age continue to apply to every mission flown today. The Hubble Space Telescope, which has been operating since 1990, cycles between sunlit and shadowed portions of its orbit roughly 15 times per day. Its thermal control system must prevent the temperature variations from deforming the primary mirror, which must maintain its shape to within a fraction of the wavelength of visible light to produce the sharp images the telescope is known for. Even tiny thermal deformations would compromise the optical performance irreparably. Every minute of every day, heaters and thermal blankets work together to maintain the mirror at a stable temperature, while the external environment cycles between extremes. The Mars rovers, Spirit, Opportunity, Curiosity, and Perseverance face the particular challenge of operating on a surface where nighttime temperatures regularly fall below -100°C, and daytime temperatures can reach a few degrees above zero at the equator. The rovers use radioisotope heater units, small capsules containing naturally decaying radioactive material that generate a few watts of thermal energy regardless of the ambient conditions, to prevent their batteries and electronics from freezing during the Martian nights. The nuclear power source of the Curiosity and Perseverance rovers also generates waste heat that is carefully managed to keep the vehicles warm during cold periods and prevent overheating during warmer periods. The Pioneer 10 and 11 spacecraft, launched in the early 1970s on trajectories that would carry them out of the solar system entirely, provided direct measurements of the thermal environment of deep interstellar space as they receded from the sun. Their onboard instruments grew progressively colder as the solar radiation decreased with increasing distance. By the time they were several billion miles from the sun, beyond the orbit of Neptune, the solar energy input to their surfaces had dropped to a tiny fraction of what it was at Earth's orbital distance. Without the radioactive thermal generators powering their systems, the instruments would have frozen long before reaching those distances. The Voyager 1 and Voyager 2 spacecraft, launched in 1977 and still operational more than 4 decades later, carry radioisotope thermoelectric generators that convert the heat from decaying plutonium dioxide into electricity. The generators lose roughly 4 watts of electrical output per year as the radioactive material decays. By the time this script describes them, the generators have been running for decades and continue to power a handful of instruments aboard each spacecraft. The spacecraft themselves are now in interstellar space, beyond the heliopause where the solar wind gives way to the interstellar medium. They are experiencing the thermal environment of the space between the stars directly. The temperature of their outer surfaces is determined almost entirely by the balance between the heat generated by their onboard systems and the rate at which that heat radiates away into the void. These engineering stories are not digressions. They illustrate the same physical principles at work in the cosmos at large. Thermal management in space is thermal management in the cold. Every solution developed for spacecraft thermal control is a solution to the problem of maintaining a pocket of warmth against the indifference of a vast cold environment. The spacecraft are small stars in a sense, concentrating and managing energy to maintain conditions very different from the void that surrounds them. The human body does the same thing on a biological scale. Maintaining a core temperature of approximately 37 degrees Celsius requires continuous metabolic activity that generates heat to offset the continuous loss of heat through radiation, conduction, and convection to the surrounding environment. A person at rest generates roughly 80 watts of metabolic heat, roughly the output of an old incandescent light bulb. In cold environments, shivering increases this to several hundred watts. The body is not simply warm in a cold world. It is a machine that actively produces warmth against the constant tendency of the environment to equilibrate. The moment metabolism ceases, the body begins cooling toward the ambient temperature. Life is not a state of warmth, it is a process of warmth generation. The physics of heat loss from a human body in space combines all 3 mechanisms in an interesting way. In the vacuum of orbit, conduction and convection are absent. The body radiates heat into the void as infrared photons. If exposed to sunlight, it simultaneously absorbs solar radiation. The net heat flow determines whether the person overheats or freezes. A spacesuit is therefore a sophisticated thermal regulation device, not merely a pressure vessel. It must prevent overheating in direct sunlight while preventing dangerous cooling in shadow across a temperature range that spans several hundred degrees, using materials and systems that add minimal weight and require minimal power. The suits used by NASA astronauts for spacewalks contain multiple layers of insulation made from aluminized mylar and other low-emissivity materials that reflect radiation and reduce heat transfer. Liquid cooling and ventilation garments circulate water through tubes against the skin to absorb excess body heat generated by physical exertion. Temperature sensors monitor suit and body temperature continuously. If the cooling system fails, the suit can overheat within minutes. If the heating system fails in shadow, dangerous cooling can occur. The margin for error in the thermal systems of a spacesuit is very small. All of this engineering, from Sputnik to modern spacesuit design, represents human ingenuity applied to the fundamental challenge of maintaining warmth in an environment that provides no support for it. The universe offers no insulation, no buffer, no automatic moderation. Every warm thing in space is warm because something is actively maintaining its temperature against the tendency toward thermal equilibrium with a cold environment. On Earth, that challenge is partially handled by the atmosphere and the ocean, which provide thermal inertia that prevents rapid temperature changes, moderate the extremes of direct sunlight and shadow, and redistribute heat from warm regions to cold ones. The planet itself is a thermal regulation system of extraordinary sophistication. And the fact that it has maintained conditions hospitable to liquid water for approximately 4 billion years is itself a remarkable outcome of the conditions under which Earth formed and the processes that have governed its evolution. The carbonate-silicate cycle, for example, is a geological thermostat that has operated over hundreds of millions of years to regulate Earth's surface temperature. Carbon dioxide, a greenhouse gas, is added to the atmosphere by volcanic activity and removed by weathering of silicate rocks, a process accelerated in warmer temperatures because chemical reactions proceed faster when it is warm. If the planet warms, weathering increases, removing more carbon dioxide from the atmosphere and reducing the greenhouse effect, which cools the planet. If the planet cools, weathering decreases, carbon dioxide builds up from volcanic sources, strengthening the greenhouse effect and warming the planet. This negative feedback loop has prevented Earth from freezing permanently or overheating catastrophically through several ice ages and periods of elevated volcanic activity. Without it, Earth's climate would be dramatically less stable than it has been, and the long history of biological evolution that ultimately produced complex life would likely have been interrupted. Venus provides the counterfactual. Venus is slightly smaller than Earth and receives more solar radiation because it orbits closer to the Sun. At some point in its early history, perhaps when the Sun was younger and dimmer, Venus may have had liquid water on its surface. But as the Sun gradually brightened, Venus crossed a thermal threshold. Enough water evaporated into the atmosphere to trigger a runaway greenhouse effect. Water vapor is a powerful greenhouse gas. As more water evaporated, the greenhouse effect strengthened. As the greenhouse effect strengthened, temperatures rose further. As temperatures rose, more water evaporated. The positive feedback loop drove Venus to its current state, a surface temperature of roughly 465 degrees Celsius, hot enough to melt lead, under an atmosphere 90 times denser than Earth's, composed almost entirely of carbon dioxide with clouds of sulfuric acid. The same physical processes that maintain Earth's temperature within a livable range failed catastrophically on Venus. The difference between the two planets illustrates how fine the line between habitable and uninhabitable can be, even for planets of similar size orbiting the same star at nearby distances. Mars provides a different kind of cautionary tale. Mars is smaller than Earth and formed at a greater distance from the Sun. Its smaller mass means it retained less internal heat from its formation. As the Martian interior cooled, the convection that drove its magnetic dynamo weakened and eventually stopped. Without a strong magnetic field to deflect the solar wind gradually eroded Mars's atmosphere over hundreds of millions of years. As the atmosphere thinned, the greenhouse effect weakened and the planet cooled. The liquid water that once flowed across the Martian surface froze, largely into the polar ice caps and permafrost, or escaped to space. Mars today is a frozen desert with an atmosphere only 1% as dense as Earth's, where temperatures average approximately -60 degrees Celsius and surface water in liquid form cannot exist. The geological evidence, including dry river channels, ancient lake beds, and mineral deposits that require liquid water to form, indicates that Mars was warm and wet for a period early in its history. Whatever life might have begun there, if any did, would have faced increasingly hostile conditions as the planet cooled and its protective atmosphere eroded. Mars stands as a reminder that warmth, once lost, cannot necessarily be recovered. Earth itself has come close to losing its habitability on multiple occasions. During the snowball Earth, events that occurred between approximately 700 and 630 million years ago, the planet may have been almost entirely covered in ice, with average global temperatures near or below the freezing point of water. The trigger for these events is debated, but the escape from them depended on volcanic carbon dioxide accumulating in the atmosphere over millions of years, gradually strengthening the greenhouse effect until temperatures rose enough to begin melting the ice. Once melting began, a positive feedback operated in the other direction, as exposed dark ocean absorbed more sunlight than the reflective ice it replaced, amplifying the warming. The planet transitioned from near total glaciation to warm conditions in a geologically rapid period. Life survived these events, apparently sheltering in pockets of liquid water near hydrothermal vents, or in regions where ice thinned enough to allow some sunlight to penetrate. The persistence of life through the snowball Earth events suggests a remarkable resilience, but the events themselves illustrate how close the Earth system has come to thermal states incompatible with complex surface life. The history of Earth's temperature is therefore not simply a story of stable, habitable conditions maintained effortlessly. It is a story of narrow escapes, geological regulation, stellar luck, and the particular physical properties of water that allow it to remain liquid across an unusually wide range of temperatures relative to other common compounds. Life on Earth evolved in the context of all of these constraints and contingencies. Its existence is not evidence that warm, habitable conditions are common in the cosmos. It is evidence that warm, habitable conditions, when they do arise, can sustain the development of remarkable complexity. Whether similar conditions exist elsewhere in the galaxy or the universe remains one of the central unsolved questions of modern science. The detection of exoplanets over the past 3 decades has transformed this from a purely philosophical question to an empirical one. The Kepler Space Telescope, which operated from 2009 to 2018, monitored the brightness of over 150,000 stars continuously, looking for the tiny periodic dips in stellar brightness caused by a planet crossing in front of the star. The mission detected over 2,500 confirmed exoplanets and identified thousands more candidates. The results painted a picture of a galaxy teeming with planets. Nearly every star appears to have at least one planet. The average number of planets per star in the Milky Way is estimated at greater than 1. Many stars have multiple planets. Rocky planets in the habitable zones of their host stars appear to be relatively common, with estimates suggesting roughly 1 in 5 to 1 in 8 Sun-like stars hosts a rocky planet in the habitable zone. But as discussed earlier, orbital placement within the habitable zone is only the beginning of the list of conditions required for a planet to actually sustain warm, habitable conditions. The fraction of habitable zone planets that also have the right atmospheric composition, the right magnetic field, the right geological activity, and the right history of asteroid and comet bombardment to maintain liquid water over billions of years is unknown and could be very small. The TESS mission, the Transiting Exoplanet Survey Satellite, launched in 2018, is conducting a broader survey of nearby stars, identifying exoplanet candidates that can be studied in detail by follow-up instruments. The James Webb Space Telescope, with its unprecedented sensitivity to infrared radiation, is capable of studying the atmospheres of some nearby exoplanets by observing how starlight filters through those atmospheres during transits. The chemical composition of an exoplanet's atmosphere can reveal whether certain molecules that could be produced by biological processes are present, providing indirect evidence of possible biological activity. This research program is in its early stages. The atmospheres of a handful of nearby exoplanets have been studied in some detail, but the instruments and techniques needed to detect definitive signatures of biological activity on an Earth-like planet orbiting a Sun-like star at a distance of tens of light years do not yet exist. Developing those capabilities will likely take decades and will require new space missions dedicated to direct imaging of exoplanets, separating the faint reflected light of a planet from the overwhelming glare of its host star. Whether life exists elsewhere, and whether it exists anywhere else in a form that experiences the warmth it depends on as something worth noticing, remains unknown. But the thermal reality of the cosmos frames the question in a specific way. The universe does not naturally produce warm places. The few that exist are the result of specific physical conditions that must align and persist. Finding evidence of life elsewhere would not tell us that the universe is hospitable to life. It would tell us that the narrow conditions hospitable to life have been met in at least one other location, which would be a remarkable discovery but would not change the fundamental thermal character of the cosmos. The warmth is here. It is real. It is extraordinary in the context of everything that exists. And the question of what it means to be warm in a cold universe, temporarily, locally, improbably, remains one of the most profound that any thinking being has ever been in a position to ask. Physics does not answer that question. It simply establishes the conditions within which any answer must be formulated. The conditions are clear. The temperature of the universe is 2.7 Kelvin across the vast majority of its volume and most of its duration. The warm exceptions are small, scattered, and temporary. The cold is the baseline state, the default, the universal average toward which everything tends, and from which the brief, bright, warm era of stars and planets and life represents a departure that will not last. The universe began in fire. It will end in cold. And somewhere in the middle, on a warm, rocky planet orbiting an ordinary star in an unremarkable galaxy. The descendants of ancient chemistry became aware of their own improbability and looked up at the stars and asked how cold the space between them really is. The answer is almost incomprehensibly, overwhelmingly, permanently cold. And the asking of the question is itself a reminder of how extraordinary it is to be here at all. There is one more dimension of cosmic cold worth examining carefully, because it connects the physics we have discussed to some of the most active areas of current research in cosmology and fundamental physics. That dimension is dark energy, and its relationship to the thermal future of the universe is both direct and deeply strange. Dark energy is the name given to the component of the universe responsible for the observed acceleration of cosmic expansion. When astronomers in the late 1990s used observations of distant Type Ia supernovae to measure how quickly the universe was expanding in the past compared to the present, they expected to find that the expansion was slowing down. Gravity, acting on all the matter in the universe, should pull things back together over time, decelerating the expansion that began with the Big Bang. Instead, they found the opposite. The expansion was accelerating. The distant supernovae were dimmer than they should have been if the universe were decelerating, meaning they were farther away than expected. The universe was not just continuing to expand. It was expanding faster and faster with every passing billion years. The two teams that made this discovery, led by Saul Perlmutter and by Brian Schmidt and Adam Rees, shared the Nobel Prize in Physics in 2011 for what remains one of the most surprising observational results in the history of cosmology. The acceleration requires a source. Some form of energy must be pushing space apart against the pull of gravity. This energy, dubbed dark energy, constitutes approximately 68 to 72% of the total energy content of the universe, according to current measurements. It is not associated with any known particle or field in the standard model of particle physics. It does not cluster with matter. It does not dilute as the universe expands. It appears to be a property of space itself, an energy density that remains constant as space grows. The simplest mathematical description of dark energy is Albert Einstein's cosmological constant, a term he introduced into his equations of general relativity in 1917 for other reasons, and later called his greatest blunder, only for it to be vindicated by observation 8 decades later. What dark energy means for the thermal future of the cosmos is straightforward in its consequence and staggering in its implications. If dark energy remains constant as the universe expands, the expansion will continue accelerating forever. There is no mechanism within known physics that will bring the expansion to a halt or reverse it. The universe will grow without limit, and as it does, the objects within it will be pushed farther and farther apart. On the largest scales, galaxy clusters will remain gravitationally bound, as they are today. But the filaments and sheets connecting them will thin and eventually dissolve as the space between them expands faster than gravity can maintain structure. Individual galaxies and galaxy clusters will become isolated islands of matter in an otherwise empty and growing void. Stars within those galaxies will continue to burn for as long as their fuel allows, but no new material will arrive to replenish depleted reserves. The Milky Way and Andromeda galaxy, which are currently on a collision course and are expected to merge in roughly 4 to 5 billion years, will eventually settle into a single large elliptical galaxy. That merged galaxy, along with the other members of the local group, will persist as a gravitationally bound system while the rest of the universe recedes beyond reach. Beyond the local group, the accelerating expansion will push every other galaxy cluster beyond the cosmological horizon, the boundary beyond which light can no longer reach us, because the intervening space is expanding faster than light can cross it. This is not a violation of the principle that nothing travels faster than light. Space itself is expanding, not objects moving through it. The effect is that the observable universe will shrink over billions of years. Distant galaxies that are visible today will eventually be carried beyond the horizon, their light redshifted to zero energy, forever lost to any observer remaining in the local group. The cosmic microwave background photons from regions now outside our observable universe have already been lost in this way. The observable universe is not a fixed quantity. It is shrinking as dark energy accelerates the expansion. The night sky of the far future will be emptier, not just because stars will have burned out, but because the universe itself will have removed most of its contents from view. The thermal consequence of accelerating expansion is that it accelerates the cooling. The cosmic microwave background will be stretched to even longer wavelengths and lower temperatures faster than it would in a decelerating or coasting universe. The isolated remnant galaxy clusters of the distant future will see a background temperature that is a tiny fraction of 2.7 Kelvin, a cold so extreme that no natural process within those clusters will be able to warm the surrounding void in any meaningful sense. The nature of dark energy itself remains one of the deepest unsolved problems in physics. Whether it truly is a cosmological constant, a fixed property of space, or whether it is a dynamic field that varies over time and space, is not yet established. If dark energy is dynamic, it could in principle evolve in ways that change the ultimate fate of the universe. Some theoretical models propose forms of dark energy that grow stronger over time, eventually tearing apart not just the large-scale structure of the cosmos, but galaxies themselves, and then stars, planetary systems, and ultimately individual atoms in an event called the Big Rip. In the Big Rip scenario, the expansion of space would grow so rapid that even the electromagnetic forces holding atoms together would be overwhelmed by the stretching of space, and matter would be dissolved into its fundamental constituents in the final moments before the endpoint. Other theoretical models propose that dark energy might weaken over time and eventually reverse, causing the universe to begin contracting rather than expanding. In such a scenario, the Big Crunch, the universe would eventually collapse back to a state of extreme density and temperature, the reverse of the Big Bang. The conditions at the end of such a collapse would resemble those of the earliest moments of the universe, extreme heat and density rather than extreme cold and emptiness. Current observations suggest that dark energy behaves consistently with the cosmological constant, meaning it does not vary significantly with time. But the measurements are not yet precise enough to rule out small variations. Future surveys using arrays of thousands of galaxies to precisely map the history of cosmic expansion, such as the Euclid mission launched by the European Space Agency in 2023, and the Vera Rubin Observatory conducting its legacy survey of space and time, will constrain the behavior of dark energy with far greater precision than currently available. These results will determine whether the cosmological constant is the right description or whether the universe's dark energy has an identity more complex than a fixed property of space. Until those measurements are made and analyzed, the ultimate thermal fate of the universe remains uncertain in its details, though its broad direction is clear regardless of the specific behavior of dark energy. The universe is cold and getting colder. The warm places are temporary and getting fewer. The cold does not threaten the warm places in any active sense. It simply waits, as it has always waited, as it will always wait, across timescales that render the concept of patience meaningless. There is also the question of what happened before the Big Bang, or more precisely, whether that question has any meaning. In the standard cosmological model, time itself began with the Big Bang. Asking what came before is like asking what is north of the North Pole. The question applies a concept, the direction of before, to a regime where that concept has no reference frame. Yet this answer, while mathematically defensible, leaves many physicists unsatisfied. Various theoretical frameworks attempt to address what might have preceded or given rise to the Big Bang. String theory, loop quantum cosmology, and various other approaches to quantum gravity suggest different possibilities. Some models propose that the Big Bang was not a true beginning, but a bounce, a collapse of a previous universe that reached maximum compression and then rebounded into expansion. If such a bounce occurred, the thermal conditions at the moment of maximum compression might resemble those of the earliest moments of the Big Bang we know, extreme heat and density, and the current cosmic expansion and cooling might be the aftermath of that bounce. Other models, including some versions of eternal inflation, propose that our observable universe is one of an enormous or infinite number of bubble universes, each initiated by a local region of quantum fluctuations within a larger inflating background spacetime. In this picture, the Big Bang of our universe was a local event within a much larger structure, and other universes with other physical constants and other thermal histories exist beyond our cosmological horizon. forever out of reach. The cold of our universe, the 2.7 Kelvin background, and the accelerating expansion would be properties specific to our bubble, the result of the particular way our local region of spacetime began, not a universal truth about all possible universes. These ideas are at the frontier of theoretical physics and are not yet testable with current technology. They may not be testable with any technology in principle, depending on how the theories develop. But they illustrate the depth of the questions that the simple observation of cosmic cold raises when followed to its logical conclusions. The cold is not just a measurement. It is a window into the deepest unsolved problems in physics, cosmology, and perhaps even philosophy. What is the ultimate nature of dark energy? What happened before the Big Bang? Are there other universes with other temperatures? Is the emergence of warm, complex, self-aware regions of the cosmos an inevitable consequence of physical law or a rare accident of specific initial conditions? These questions do not yet have answers. Some may never have answers, but they are asked from within a warm pocket of the universe that has lasted long enough and that produced matter complex enough for the asking to occur. Future space missions will address some of the observational pieces of this puzzle. The next generation of cosmic microwave background experiments, currently being planned and developed, will map the polarization of the background radiation with unprecedented sensitivity. Polarization patterns in the background carry information about the dynamics of the earliest universe that temperature measurements alone cannot provide. If inflation occurred, it should have produced a specific pattern of gravitational waves that left a detectable imprint on the polarization of the cosmic microwave background. Detecting this signal would be one of the most important results in the history of observational cosmology, providing direct evidence about the physics of the first tiny fraction of a second after the Big Bang. Ground-based and space-based gravitational wave observatories will also extend our reach into the thermal history of the universe in new ways. Gravitational waves, ripples in space-time produced by the collision and merger of massive objects, carry information that does not interact with matter the way light does. Gravitational wave backgrounds from the earliest universe, produced by processes that occurred before recombination when the universe was still opaque to light, could in principle be detected. If they are, they would open a window into the universe's thermal history from epochs that no electromagnetic observation can reach. The science of cosmic cold, from the 2.7 Kelvin background to the physics of stellar death, from the engineering of spacecraft thermal systems to the deep theoretical questions about the nature of dark energy, is not a closed chapter. It is an ongoing investigation into the most fundamental properties of the universe we inhabit. What is established beyond reasonable doubt is the basic thermal portrait of the cosmos. The universe is cold. Nearly all of its volume sits at or near the 2.7 Kelvin floor set by the remnant radiation of its own birth. The hot exceptions, stellar interiors, accretion disks, supernova remnants, occupy a fraction of cosmic volume that rounds to zero by any practical measure. The warm, habitable, life-sustaining conditions found on Earth represent a further subset of those exceptions. Constrained by a long list of requirements that must simultaneously be met and maintained over geological timescales. The warm era, the stelliferous period during which stars burn and planets orbit and biology operates, is a brief window within a much longer timeline of darkness and cold. Before the first stars, the universe was cooling from its hot beginning. After the last stars, the universe will cool toward whatever minimum temperature the expansion of space ultimately allows. The warmth is sandwiched between two expanses of cold, one in the past and one in the future, each vastly larger in duration than the warm interval between them. This is the thermal reality of the cosmos as physics currently understands it. It is not a comfortable picture in the sense of offering reassurance that the universe is hospitable. But it is an honest picture, derived from observation, measurement, and the application of physical laws that have been tested with extraordinary precision across a wide range of conditions. The universe owes us no comfort. It operates according to laws that are indifferent to the existence of anything within it. Those laws, followed precisely, produce a cosmos that is overwhelmingly cold, briefly and locally warm, and heading irreversibly toward a colder equilibrium. The warmth that exists now, including the warmth of Earth, of its oceans and atmosphere, of its biology, of every mind that has ever contemplated the night sky, exists because of a chain of specific physical and historical circumstances that happened to produce these conditions in this place at this time. That chain was not inevitable, it was not guaranteed, and it will not persist indefinitely. The cold of space is the context, the warmth is the event, and the event, however extraordinary it is, happens entirely within the cold. Understanding this, clearly and accurately, changes how the night sky looks. Each point of light is a local exception to the universal rule, a nuclear furnace fighting the same cosmic cold that presses in from every direction across every scale. The darkness between the stars is not empty in the trivial sense. It is full of the oldest light in the universe, stretched to near invisibility by billions of years of expansion, maintaining the coldest sustained temperature that nature knows how to produce. The study of that cold, and of the rare warm places embedded within it, is one of the great ongoing investigations of human science. The measurements grow more precise with every passing year. The theoretical frameworks grow more sophisticated. The questions grow deeper, and all of it is done from within a warm pocket of the universe, fragile and temporary, sustained by a particular star's particular output for a particular period of cosmic history, looking outward into the cold and asking what it means. The cold is the answer to most questions about what the universe is like in general. The warm is the context in which the questions get asked. Both of those facts are worth holding in mind when looking up at the stars on a clear night and feeling the faint chill of the air, a chill that is, compared to the universe beyond, indistinguishable from perfect warmth. To bring together everything discussed so far with a sharper focus on what the measurements actually mean when translated into human terms, consider one final journey through the temperature landscape of the universe, beginning at the coldest extremes and working upward to the hottest. Start at the floor, absolute zero, 0 Kelvin. No naturally occurring process produces this temperature. It is the theoretical boundary below which nothing can exist. Even in the most advanced physics laboratories on Earth, where scientists use combinations of laser cooling, evaporative cooling, and magnetic trapping to cool samples of atoms to billionths of a Kelvin, the absolute limit remains out of reach. The Bose-Einstein condensate, a state of matter predicted by Satyendra Nath Bose and Albert Einstein in the 1920s, and first experimentally realized in 1995 by Eric Cornell and Carl Wieman, forms when atoms are cooled to temperatures within a few hundred billionths of a Kelvin of absolute zero. At those temperatures, the individual atoms lose their distinct quantum identities and behave as a single quantum entity, a macroscopic expression of quantum mechanical effects that normally manifest only at the atomic scale. These experiments represent the coldest objects ever deliberately produced by human beings. They are also entirely artificial, maintained by continuous energy input and lasting only fractions of a second to a few minutes in most experiments before warming back to ambient conditions. 2.7 Kelvin is the cosmic floor above absolute zero. It is where the universe settles when left to its own devices, far from any local energy source. The cosmic microwave background photons that maintain this temperature are the most numerous photons in the universe by far. For every photon of visible starlight in the cosmos, there are roughly 1 billion microwave background photons. The universe is not predominantly a place of starlight. It is predominantly a place of microwave background radiation so faint and so cold that it borders on nothing. 10 Kelvin is the temperature of the coldest dense molecular cloud cores, the regions inside nebulae where new stars will eventually be born. These clouds contain water ice, carbon monoxide ice, and complex organic molecules frozen onto the surfaces of dust grains. The chemistry in these cold regions is not the chemistry of liquid water and dissolved ions that powers biology on Earth. It is a chemistry of ices and surface reactions, operating at temperatures where most of the molecules familiar to biology would be frozen solid. 77 Kelvin, the boiling point of liquid nitrogen. This temperature feels inconceivably cold by everyday standards. Skin contact with liquid nitrogen causes immediate frostbite. Yet the universe achieves and vastly exceeds this level of cold across the majority of its volume without any effort whatsoever. 184 Kelvin, Earth's coldest natural temperature, still 68 times warmer than the cosmic background. 258 Kelvin, Average surface temperature of Mars. Cold enough to freeze carbon dioxide at the poles, cold enough to make liquid water impossible at the surface under current conditions. 288 Kelvin, Earth's average surface temperature. This number, 15 degrees Celsius, represents the narrow thermal sweet spot in which all known life has evolved and continues to operate. 310 Kelvin, human body temperature. The temperature that the human nervous system evolved to maintain with extraordinary precision, because the enzymes, proteins, and DNA that power biological function operate optimally within a few degrees of this value. 738 Kelvin, the surface temperature of Venus. Hot enough to melt lead, hot enough to destroy electronic equipment within hours, maintained not by proximity to the sun alone, but by the runaway greenhouse effect that transformed a potentially habitable world into a hellscape. 5,778 Kelvin, the surface temperature of the sun. The temperature at which the sun's photosphere radiates energy that crosses 93 million miles of vacuum to warm Earth, drive weather, and power photosynthesis. 15 million Kelvin, the temperature of the sun's core, where hydrogen fusion occurs. 100 million Kelvin, the approximate temperature at which helium fusion ignites in the cores of aging stars after their hydrogen supply has been depleted. Several billion Kelvin, the temperatures at the centers of the most extreme stellar environments in the collapsed cores of massive stars moments before a supernova explosion. 10 trillion Kelvin, the temperature of the universe at roughly 1 microsecond after the Big Bang, when protons and neutrons were first condensing out of the quark-gluon plasma that preceded them. 10 trillion Kelvin, the temperature of the universe in the first tiny fraction of a second, when the observable cosmos occupied a volume smaller than an atomic nucleus and matter as we know it did not yet exist in any recognizable form. This is the temperature range over which the universe has operated during its 13.8 billion year history. From the incomprehensible heat of its birth to the near absolute cold of its current cosmic average, spanning more than 40 orders of magnitude. Every familiar temperature in human experience occupies a tiny slice of this range. The entire range of conditions that support life on Earth, from the boiling point of water to the coldest survivable temperature for any known organism, spans less than 300 Kelvin, a range that looks like a single point on a logarithmic scale running from 0 to 10 trillion trillion. The universe passed through the temperature range compatible with life in its very earliest moments, and has been cooling away from it ever since. The conditions that exist on Earth today represent not the natural state of cosmic evolution, but a specific local environment maintained by a particular stellar heat source in a particular cosmic era. Conditions that are unusual even within the brief stelliferous period of cosmic history, and that will not persist on any cosmologically significant timescale. The measurements that support all of this are among the most precisely confirmed results in observational science. The temperature of the cosmic microwave background is known to 4 significant figures. The age of the universe is known to better than 1%. The composition of the universe in terms of ordinary matter, and dark energy is constrained to percent-level precision. The patterns of temperature fluctuations in the microwave background have been mapped across the entire sky at angular resolutions of a fraction of a degree. The large-scale distribution of galaxies has been traced across billions of light-years. The thermal histories of stellar evolution are understood in detail from first principles and confirmed by observations across the full range of stellar masses and ages. This is not speculation. It is not philosophy dressed as science. It is measurement and the application of physical laws tested with extraordinary precision, extrapolated to cosmic scales with tools developed over more than a century of observational and theoretical work. The result of all this measurement is a clear picture. The universe is cold, not in any poetic sense, not as a metaphor. Cold in the most precise, measurable, thermodynamically rigorous sense that physics provides. 2.7 Kelvin across the overwhelming majority of its volume and most of its future duration. Brief, scattered, temporary exceptions burning in the cold, each one a local and limited victory over the universal equilibrium. And somewhere among those exceptions, on a rocky world, at the right distance from the right star, in the right era of cosmic history, matter arranged itself into patterns complex enough to ask the question, The question and the answer are both extraordinary. The question because it requires a universe that has produced the conditions for curiosity to exist. The answer because it reveals how improbable and precious those conditions are in the context of everything else that exists. The cosmic microwave background is still filling this room right now. Roughly 400 photons per cubic centimeter, each carrying an energy corresponding to 2.7 Kelvin, passing through you and through the walls around you without interacting with any atom in your body. They have been traveling since the universe was 380,000 years old. They carry within them the memory of a universe that was everywhere hot and bright and opaque. A universe that has since cooled by a factor of over 1,000, stretched itself into transparency, grown dark across most of its volume, and produced in scattered warm pockets the stars and planets and the brief era of life and thought now occurring somewhere in its midst. The cold is not the enemy of the warm, it is the context. It is what the warm exists within. And the warm, however temporary, is where the questions get asked, and where the measuring is done, and where the wonder, if the universe allows anything like wonder, actually occurs. That may be the most remarkable fact of all. One aspect of cosmic cold that deserves closer attention is the role that the expansion of the universe plays not just in cooling the microwave background, but in shaping the entire thermal landscape of the cosmos over time. The expansion is not merely a backdrop. It is the driving force behind the thermal history we have traced, and understanding it in more detail reveals why the cold is so inevitable and so total. When Edwin Hubble demonstrated in 1929 that the light from distant galaxies was systematically shifted toward longer, redder wavelengths in proportion to their distance, the implication was clear. The galaxies were receding from us, and the farther away they were, the faster they were receding. This was not a case of galaxies moving through space like objects thrown outward from an explosion. Space itself was expanding, carrying the galaxies with it. The most useful analogy is dots drawn on the surface of a balloon being inflated. Each dot moves away from every other dot as the balloon expands, not because the dots are moving across the surface, but because the surface itself is growing. The rate of this expansion is described by the Hubble constant, approximately 67 to 73 kilometers per second per megaparsec according to current measurements, meaning that a galaxy 1 megaparsec, roughly 3.26 million light-years away, is receding at roughly 70 kilometers per second due to expansion alone, while a galaxy 2 megaparsecs away is receding at roughly 140 kilometers per second. The exact value of the Hubble constant is currently the subject of an active and unresolved tension in cosmology. Measurements derived from the cosmic microwave background using the Planck satellite yield a value near 67.4 kilometers per second per megaparsec. Measurements derived from the distances and recession velocities of nearby galaxies using methods like Cepheid variable stars and Type Ia supernovae consistently yield values near 73 kilometers per second megaparsec. This discrepancy, known as the Hubble tension, is large enough to be statistically significant and has not been resolved by identifying errors in either measurement method. It may indicate that the standard cosmological model requires modification, or that one or both sets of measurements have systematic errors not yet identified. Whatever the exact value of the Hubble constant, the expansion it describes has a direct thermal consequence. Any photon traveling through expanding space is stretched by the expansion. Its wavelength increases in proportion to the factor by which the universe has grown since the photon was emitted. Since the energy of a photon is inversely proportional to its wavelength, a photon stretched to longer wavelengths carries less energy. And a collection of photons with lower average energy corresponds to a lower temperature. The expansion of the universe is therefore a perpetual cooling mechanism. Every photon in the universe is being cooled by the expansion at every moment. Not through any interaction with matter, but through the stretching of space itself. This mechanism applied to the cosmic microwave background photons has reduced their temperature from 3000 Kelvin at the time of recombination to 2.7 Kelvin today, a reduction by a factor of roughly 1100 corresponding to the factor by which the universe has expanded since that time. The same mechanism applied to the photons emitted by stars and other hot objects means that even the light from distant stars arrives at Earth slightly cooler, slightly redder than when it was emitted. For nearby stars, the effect is negligible. For very distant galaxies observed billions of years after their light was emitted, the redshift is dramatic, shifting ultraviolet radiation into the visible spectrum and visible light into the infrared. The expansion does not just cool photons, it also dilutes the density of matter. A fixed number of atoms spread through a growing volume means a decreasing number of atoms per unit volume over time. This dilution reduces the thermal effect of any hot gas as the universe expands, because the energy carried by the gas is spread over an ever larger volume. The warm-hot intergalactic medium, already so sparse that it contributes negligibly to the thermal environment of any object passing through it, becomes more dilute with every passing billion years. Its thermal influence, already negligible, becomes progressively more negligible. The only component of the universe's energy budget that does not dilute with expansion is dark energy. If dark energy is truly a cosmological constant, a fixed energy density of space itself, then as space expands, the total amount of dark energy increases in proportion to the increasing volume. This is the energy source that drives the acceleration. As the universe grows, it contains more dark energy, which drives faster expansion, which increases the volume, which increases the total dark energy, which drives still faster expansion. The feedback is self-reinforcing, and there is no natural mechanism within the known laws of physics to stop it. The consequence for cosmic temperature is that the acceleration amplifies the cooling, not just by stretching existing photons faster, but by guaranteeing that the galaxies and their heat sources are separated from each other at an accelerating rate, reducing the probability that any energy produced in one location can ever reach another location. The cosmic isolation that dark energy enforces is thermal isolation. The warm places will grow more isolated from each other over time, each sealed within a shrinking observable horizon, each radiating its heat into a void that grows larger and colder with every passing moment. On the longest timescales, the only objects generating any heat in the universe will be the slowly evaporating black holes, producing Hawking radiation at temperatures inversely proportional to their mass. A stellar mass black hole evaporates at a temperature of roughly 60 billionths of a Kelvin, far colder than the current cosmic background. As it loses mass through evaporation, its temperature rises, but only in the very final stages of evaporation does the temperature climb significantly above the background temperature of the era. By the time the last black holes are evaporating, the cosmic background temperature will itself be so low that the thermal radiation from even a small evaporating black hole will briefly represent the warmest thing in the cosmos. Then it too will be gone. After the last black hole has evaporated, the universe will contain nothing but isolated particles, primordial photons stretched to unimaginable wavelengths, and the fading thermal radiation from the evaporation events. The entropy of the universe will be at its maximum. No structure will remain. No temperature gradient will exist to drive any process. The universe will have reached what physicists call the heat death, not a state of intense heat, but a state of total thermal equilibrium, where no energy flows from any source to any sink, because there are no sources and no sinks, only a featureless, maximally disordered expanse at the lowest temperature the universe can achieve. This is the ultimate destination implied by the second law of thermodynamics applied to a finite universe. The law that says entropy, the measure of disorder, always increases in isolated systems, ensures that the organized structures we see today, stars, planets, ecosystems, civilizations, are transient. They are local decreases in entropy maintained by the continuous flow of energy from hot sources to cold sinks. Remove the sources or allow the sinks to fill to equilibrium, and the structures disappear. The universe as a whole is the ultimate isolated system. Its entropy has been increasing since the Big Bang, and will continue increasing until it reaches its maximum, at which point no further change of any kind is possible. The warmth of the present era is a consequence of the low entropy of the early universe. The Big Bang produced a state of extraordinarily high organization, not because the early universe was simple, but because its energy was highly concentrated. Concentrated energy is low entropy energy. As that energy has spread out through the expanding cosmos, entropy has increased, and the universe has moved toward the equilibrium that thermodynamics demands. Stars are engines that accelerate this process locally while experiencing it globally. Life is a more elaborate version of the same process, building temporary order by consuming energy and producing heat. Consciousness is perhaps the most complex local ordering process known, built on biology, which is built on chemistry, which is built on atomic physics, which is all powered by the flow of energy from the hot sun to the cold void. When that flow eventually ceases, when the last hot source exhausts itself, the universe will complete its journey from the maximum order of its beginning to the maximum disorder of its end. The temperature gradient that drives everything will be gone. The cold will be all that remains. This is not a tragedy in any cosmic sense. The universe does not have preferences about its own state. It does not mourn the loss of stars or the end of biology. It simply follows the laws of physics, which lead inexorably from the concentrated energy of the Big Bang to the diffuse thermal equilibrium of the far future. The only beings for whom this trajectory might seem significant are the beings who arose from within it, who developed the capacity to understand it, and who now contemplate what it means to be a temporary local exception to the universal trend. The significance, if it exists, is in the contemplation itself. Not in any external validation from a universe that offers none, but in the fact that the physical processes of a cooling cosmos produced, at least once, the conditions for a part of it to become aware of itself and ask where it fits in the larger picture. The answer, as physics provides it, is that we fit in a warm and temporary pocket of an overwhelmingly cold and ultimately cooling cosmos. We exist during a brief era of stellar light sandwiched between longer eras of darkness. We inhabit a planet whose warmth depends on a long chain of specific conditions that history happened to produce in this location. And we will eventually be gone, along with the stars, along with the planets, along with every organized structure the universe currently contains, leaving behind a cold and silent expanse that will persist for a duration so much longer than our own that comparison becomes meaningless. None of this changes the experience of warmth. The sun is still warm. The ocean is still warm. The biochemistry that makes thought possible is still warm. The warmth is real. It is here now. And understanding that it is a rare and temporary gift of a specific cosmic moment does not diminish it. If anything, it clarifies it. The universe is cold, overwhelmingly, fundamentally, and increasingly cold. The warmth is exceptional, fragile, and temporary. And the exceptional and fragile and temporary warmth is where we are, looking up at the cold and finding it, of all things, interesting enough to measure.